Okay, so we're looking at the next problem in optimization here in Unit 6, and it says find the maximum area whose base is on the x-axis and the other two vertices are on the function f of x equals 3 cosine x. So we looked at a problem similar to this with a parabola, and so now we're going to look at the same type of problem with a cosine graph instead. So you can see that in this case the base of the rectangle is on both sides of the y-axis, and the top of my rectangle is constrained by the graph of y equals 3 cosine x. So it's still a rectangle. We're still talking about maximum area, so we're still going to be dealing with an area formula. So I'm going to start off again here, first of all, by grabbing a color here. So we're still going to start off with the area equals length times width. But this time, if we look at the area, there's a couple of different ways we could do this. And so because my graph goes to the right and left of the y-axis, I'm going to let this side be x. And I'm also going to, well, let me do this up here a little higher. I'm going to let this side of the rectangle be x. And since I'm going to the negative side, this side's also going to be positive x eventually. So I'm going to call the base of my rectangle 2x. Now you could do it with an x, but you would just have to take into account some things at the end, I believe. The height of my rectangle is still y, but y is constrained by the graph of 3 cosine x. Okay, so when I go to set up my formula here this time, I'm going to have area equals length times width. My area becomes the length, which I'm going to call the bottom. It doesn't matter, you can do either one. But my length is going to be 2x, and my width is going to be the y value. And again, I'll put it in there for a second, but immediately what I'm going to do here is I'm going to replace y. I'm going to replace y with 3 cosine x. So 3 cosine of x. And now my equation is all in terms of x. Alright, so there's nothing to distribute here. This is just, I think I could probably just, hang on a second. So I could do a little bit of simplifying here with the 2 and the 3, so I'm probably just going to go ahead and do this right now. So we'll have area equals 2x times 3 is 6x times cosine of x. Alright, so now I need to take a derivative. Okay, so I'm going to do dA dx, and let me see, I've got a little bit of room here on the left side still. So I'm going to do dA dx, and that's going to equal, and I've got a little bit of product rule going on here, so I need the derivative of the first, which is 6, times the second, which is cosine of x, plus the first, which is 6x, times the derivative of cosine, which is negative sine x. And so if I simplify this, I get 6 cosine x minus 6x sine x. Now the problem with trying to solve this is I've got 2 variables in here. Alright, so this is dA dx. But what I want to do is I want to set dA dx equal to 0 and solve this. So when I set it equal to 0, again, I can't solve this because I've got variables, I've got x's, and I've got sine x's, and I can't solve that. What I can do is I can divide both sides by 6 right now and kind of get rid of that. So I'm going to do 0 divide by 6. That's going to leave me cosine of x, and I just realized I forgot my x right there, so we'll put that back in, minus x sine x. So this is not going to be possible to solve without a graphing calculator, and so I'm going to pause for a minute, get my graphing calculator set up, and then we'll come back. Okay, so you can see by the original graph up here I am constrained, and if you think about what these points would be on the x-axis of the original graph f of x here, you're a little bit past 1.5 and negative 1.5, and since this is the graph of cosine x, these values are actually positive pi over 2 and negative pi over 2. So I'm constrained to the width of my rectangle by pi halves and negative pi halves for my width. So when I go to graph this, I only want to be looking at values up to pi halves. And so I've got my graph here already set up, and you can see that on the graph you're at positive 1 over here on the right. So 1.5 is going to be, or pi halves is going to be roughly right around this area in between 1 and 2 right here. And so what I'm looking for is I am looking for the maximum area here, and I'm looking at it between pi halves, which is again is on the left side, negative pi halves on the left side over here, all the way up to pi halves. Now this is the graph. You have to remember this is the graph of f prime of x, okay, or we called it dA dx. So dA dx is negative on the left side here up until we hit the x-axis here. So that means that our graph of f of x would be decreasing to increasing, and if I go decreasing to increasing, that's a minimum value, and then I go from a positive derivative to a negative derivative, so that's increasing to decreasing. And now so it looks like my point of intersection is going to be right over here where my maximum value happens. And so we're going to go in and use the calculator. We'll hit second, calculate, and we want to calculate that 0 on the right hand side there. So we're going to give this thing a left bound if we can here. Here we go. So we'll give it a left bound. We need a right bound. Okay, and then we'll hit enter again, and it turns out that x is 0.860, and so at that point I should have my maximum value for x. So at x equals 0.860, I should have a maximum width for x. Now you got to remember that's just one side of x here, because you remember when I drew my graph up here at the top, that's one side of x. So the base of this thing is actually going to be 2x. Alright, so we just want to keep that in mind. If I do my y value from there, I would plug in y into the, or x into the equation, the original equation. So my y value is going to equal 3 times cosine of 0.860, which means my y value is going to be 1.957, okay? And then I can write out my dimensions, okay? Now, in this case, I'm not going to do the number line because I can see from the graph that I'm going from, the derivative is going from positive to negative, which means I should have a maximum at that value. So I'm not going to bother with the number line because the graph is basically giving me my information. So my dimensions here, remember they asked for dimensions, they didn't ask for a point on this one. So my dimensions, let me learn how to spell again here. So this would be, remember my base was 2x by the height, which is y, and so if I multiply 2x, I get 2 times 0.860, and so that comes out to be 1.720, and this is a graph, there's no units attached, but if we had to, we could just say units by 1.957 units. And oh, it did say to find the maximum area, so now I would need to multiply those two guys. So area equals, and don't have that on my notes, so let's pop out a calculator here real quick, and we'll do 1.720 times 1.957, and we get an area of 3.366 units squared. Alright, so I'm going to pause for a second, grab a drink of water, and we'll be back for the next one. Okay, so here we are on the next one. It says, if you flip the page, it says a right triangle has one vertex at the origin, which you can see down here at the x and y axis. The second vertex is on the x-axis. You can see that it's labeled as C right now. and the third vertex is on the semicircle pictured. So again, this is going to be my constraint right here. It says determine the coordinates of point C, so we're looking for coordinates this time, not necessarily an area or the dimensions, that maximizes the area of the right triangle. So I'm going to label again here. My base is going to be x, my height is going to be y, but I know the height is determined by the square root of 25 minus x minus 5 squared. So at some point I'm going to be doing some substitution again here. So let me scroll up a little bit, give myself a little bit of room. I'm going to start off with the area of a triangle this time, so area equals 1/2 base times height. And substituting my variables, this would be area equals 1/2. My base is x, my height is y, but I do know that this is where y equals the square root of 25 minus x minus 5 squared. So what I want to do with that is I want to take that and I want to substitute this in for y right here. So if I rewrite, I get area equals 1/2 x times the square root of 25 minus x minus 5 squared. And now that my equation is all in terms of x, I can go ahead and take the derivative here. So this one's going to get a little bit tricky because number one, when we take derivatives, we don't deal with square roots. So I'm going to change this to area equals 1/2 x. And because this is a square root, we're going to rewrite this as 25 minus x minus 5 squared. And we're going to raise this to the 1/2 power, indicating the square root there. And then we're going to take the derivative of this. All right, so here we go. So this would be, and you can call this dA dx, or you can call this a prime. We're taking the derivative with respect to x. So a prime equals, and I've got a little bit of product rule again here. This one's going to get messy. So the derivative of the first is 1/2 times the second, so that's going to be 25 minus x minus 5 squared raised to the 1/2 power, plus the first, which is 1/2 x, times the derivative of the second. Now this is where this can get a little bit tricky because I need to bring the 1/2 down in front, so that's going to be 1/2 times the inside material, 25 minus x minus 5 squared raised to the negative 1/2 power, because we have to subtract 1. And then I need to take the derivative of the inside material. Now if you look at the inside material, I'm looking at 25 minus x minus 5 squared. So the derivative of 25 is 0, but then I'm going to drop the 2 down in front, and that's going to be negative 2 times x minus 5, and then I'm going to subtract 1 from the exponent there, so that's just going to leave me negative 2 times x minus 5 on the inside of that. Okay? Now again, right away, this is a mess. I'm not even going to try and simplify this. I'm going to go ahead and use the graphing calculator again here. So essentially what I want to do is I want to take my derivative and set it equal to 0, and I'll go from there. So I'm going to pause, set up my graphing calculator again, and we'll be back. Okay, so I've set up my graphing calculator. I've punched this equation in so you can take a look at that. Here's my calculator, and I've punched it in for y1 exactly the way it looks in the equation. The only thing I did was I multiplied the 1/2 times the 1/2 to get 1/4.
I want to leave my gloves here.
So now if I graph this, I get this picture right here. Okay, so remember, this is the derivative graph. So I'm not looking for the max height of the derivative graph. I'm looking for where the derivative goes from positive to negative. And that's right over here. Looks like right around 7 point something. So I would go to my second button again. I would hit calculate. I'm going to calculate a 0 value. and then I would scroll over there again, just like we did on the last problem. If I can get this thing to move any faster. Alright, so my left bound is going to be right here, my right bound I'm going to put right there. Whoa, 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 oh my goodness. Okay, I think I went a little too far. Okay, I'm going to have to do that again. Second, calculate, 0 value. Alright, for some reason okay, here we go. Alright, so my left bound just above the point, my right bound is going to go just below the point. I'll hit enter, and it tells me that I have a 0 value at 7.5, which means that when my derivative is equal to 0, I get x equals 7.5. Okay, so when I plug that into my equation, what are we looking here? We're actually looking for the coordinates this time of the point on the graph. So if f is equal to, or x is equal to 7.5, I need to know the y value at that coordinate right there. So my y value is going to equal the square root of 25 minus x minus 5 squared. And actually for x, I needed to plug in, I'm going to keep this, should have done this first instead of writing the whole thing out twice. 25 minus 7.5 for x minus 5 squared, and when I punch that into the calculator, I get 4.330.
Can I just see? Are my friends seeing it too?
Okay, so once we know x is 7.5, we can plug that into our function. Remember, our function was y equals, we had the square root of, let me see here, 25 minus 7.5 minus 5 squared. And if we take the square root of that, if you figure all that out, you actually end up with 4.330. And so the question above asked what are the coordinates of point C. So the coordinates of point C would be 0.5 comma 4.330. And there you go, that's the end of that problem.